welcome to our deep dive. Today, we're looking at something, well, increasingly important. Trusting AI.
Especially when it's making complex decisions, right? Like planning sequences of actions.
Exactly.
Yeah.
Think about optimizing a factory floor, or maybe planning transit routes across a whole city.
Big, complex tasks.
But the question that keeps popping up is, how do we actually know why the AI makes the choices it does?
But that sort of black box feeling.
Yeah, it can make experts, the people who really need to use these tools, a bit hesitant.
Understandably so. If you're responsible for the outcome in manufacturing or transport, you need to grasp the reasoning. It's not just optional, it's critical for trust.
And that brings us neatly to this algorithm called Monte Carlo tree search, or MCTS.
Ah, yes, MCTS. Very powerful stuff.
Super effective for those complex planning problems, where you're juggling tons of possibilities.
Definitely.
But here's the catch. MCTS builds these enormous trees of potential outcomes based on sampling and probabilities.
Right, these vast search spaces.
And trying to trace why it made one specific turn down one specific branch, it feels impossible sometimes. Like finding one leaf in a giant forest.
That's a great analogy. It captures the trade-off perfectly. You have this amazing tool for navigating complexity, but the very process it uses, exploring so many paths, makes a simple explanation really hard to get.
Okay, let's dig into that explainability problem a bit more then.
Good idea.
So we've got AI, MCTS specifically, doing heavy lifting and planning. Great.
But its thinking, if you can call it that, is buried in this huge probabilistic search.
Which, as you said, makes experts wary. Lack of transparency.
Right. And it's not just trust, it's also about, well, accountability.
Oh, good point. If a plan goes wrong.
How do you diagnose why? If you can't see the reasoning, it's tough to learn from mistakes or even validate the initial plan.
So experts are understandably cautious. They need to check the logic, spot potential issues.
You feel confident putting these AI plans into action. Without that insight, it's a leap of faith.
Okay, but here's where things get really interesting. Researchers aren't just accepting this black box, are they?
Not at all. There's a lot of work happening.
And we've found this new framework that seems really clever.
Ah, the logic-enabled LLM approach.
That's the one. It basically pairs up large language models, the AI that's amazing at generating text.
Like GPT or Llama.
Exactly. It pairs those with a rigorous logic-based system. And the goal, to translate the complex MCTS decisions into clear, plain English explanations we can actually follow.
It's a really smart combination trying to bridge that gap. You get the expressive power of LLMs, but anchored by the precision and factual grounding of logic. It's about cracking open that black box.
So how does it actually work day to day, this combination?
Well, the sources describe it like this. Say you have a question about an MCTS plan.
Okay.
The framework is designed to handle different kinds of questions really flexibly.
So not just one type of query?
No. You could ask about a specific decision after the plan has made a post hoc question.
Like why this specific action?
Exactly. Or you might ask something more general about its strategy, maybe within the context of the problem setup, like a Markov decision process or MDP.
Right. MDPs are often used for this kind of sequential decision-making under uncertainty.
They are. And the key step is how the framework handles your question. It doesn't just guess the meaning.
It does more.
Yeah, it translates your natural language question into structured logic, formal statements, variables.
Why is that translation step so important?
Because it allows the system to then systematically search the MCTS's internal data, its tree, its evaluations for concrete evidence that directly corresponds to the logic of your question.
Ah. So it ensures the answer isn't just plausible-sounding fluff, but actually grounded in what the MCTS did.
Precisely. Grounded in the environment, the constraints, the actual search process, factual consistency is key.
And then the answer comes back, not as code or logic, but
in natural language, plain English. So you ask, why send vehicle A to pick up X?
And you get back
an explanation outlining the likely factors MCTS weighed based on the evidence found using that logical query.
And you mentioned it's interactive too, not just one and done.
Right. You can ask follow-up questions. Drill down deeper if the first explanation raises more points.
Okay, that feels much more like how humans actually figure things out.
Yeah.
A conversation.
It allows for a much richer understanding, definitely. You're not stuck with one static report.
To really test this, the researchers needed a concrete problem. They used paratransit planning.
Yes. A really good, complex, real-world test case.
Can you maybe paint a quick picture of what paratransit planning involves? Especially framed as this Markov decision process, this MDP thing.
Sure. So paratransit is basically a demand-responsive transport service, often for people with disabilities or specific mobility needs.
Like shared rides, but more specialized.
Exactly. And modeling it as an MDP means thinking about it as a sequence of decisions over time, and MDP has key components. A state, what's happening right now. Locations of vehicles, active ride requests, available seats.
A snapshot of the system.
Right. Then actions, what can the controller, in this case MCTS, do? Assign vehicle X to passenger Y, reroute vehicle Z.
The choices available.
Then transitions. How does this state change based on actions and, importantly, new information like incoming ride requests? This often involves some randomness or uncertainty, which MDPs handle well.
Based on simulated demand, in this case.
Yes, based on a model of how trip requests arrive over time. And then you have constraints.
Rules like vehicle capacity.
Or time windows for pickups, wheelchair accessibility needs, things like that.
Got it. And finally,
a reward or objective function. What defines a good outcome? Minimizing wait times, maximizing completed trips, reducing vehicle mileage.
the goal the AI is trying to achieve.
Exactly. So MCTS comes in at specific points in time. They call them decision epochs, looks at the current state,
Let's snapshot.
and uses its tree search to figure out the best set of vehicle assignments to maximize that future reward, considering the constraints and the likely future requests.
So it's constantly trying to optimize the service based on the current situation and its predictions.
That's the core idea.
Okay, so when a user interacts with this explanation framework about these paratransit decisions, what kinds of questions can they actually ask? You mentioned flexibility.
Right. The researchers broke it down into two main buckets.
Okay.
Bucket 1, post hoc queries. These are questions about a plan that's already been made. You're looking back at specific MCTS decisions within that plan.
Asking why did that happen?
Pretty much. And interestingly, they identified 26 sort of predefined types of questions within this category based on common user intentions.
26 specific types. Wow, that's quite granular. What are some examples?
Oh, things like, why was this vehicle chosen over that one for this trip? Or what was the estimated wait time associated with this assignment? Or maybe, how did constraint X, like a time window, influence this specific decision? It's about the nuts and bolts of a particular choice.
Makes sense. Getting into the weeds of the plan, what's the second bucket?
That's background knowledge-based queries. These are more general.
How so?
They're less about one specific decision in the plan and more about the overall process or the context.
Like, how does MCTS generally prioritize pickups? Or what are the main objectives of this paratransit system?
Exactly. Questions about the MCTS algorithm's behavior in this domain, or about the rules and goals of the paratransit MDP itself.
And for these, there aren't predefined types.
No, because one piece of background knowledge might answer several different general questions. It's less about pinpointing one specific event in the tree.
Okay, so the framework needs to understand the question type,
Yeah.
then figure out what evidence is needed. How does it find that evidence in the MCTS tree, which we said could be huge?
Yeah, that's where the logic generation and parsing really come in. For those 26 post hoc types, the system uses examples linked to each type. These examples help guide an LLM to translate the user's specific question into that formal logical structure we talked about.
Gotcha. Using examples to get the logic right.
And then it categorizes the kind of evidence needed based on that logic.
And what are those evidence categories?
They define 3 levels. First is base level evidence.
Simple stuff.
Yeah, information you can basically just read directly from a single point, a node in the MCTS tree, a fact about a specific state or action considered.
Okay, level 2.
Derived evidence. This needs a bit more work. You have to look at multiple nodes, maybe across different branches of the tree.
Like calculating an average.
Exactly, like the average predicted wait time across several possible scenarios MCTS explored starting from a certain point.
Right. And the third level?
Logic comparison evidence. This is the most complex one.
Sounds like it.
It involves not just looking at multiple nodes, but performing multi-step calculations, and crucially, comparing different potential paths or outcomes using formal logic.
And they use something specific for that.
Yes, they mention using computation tree logic, or CTL.
CTL. Briefly, what does that let the system do?
Think of CTL as a language for expressing properties about paths through a state system, like the MCTS tree. It allows reasoning about possibilities like, is it possible to reach a state where constraint X is violated? Or Will property Y always hold true along this path?
So it enables more sophisticated reasoning about the different futures MCTS explored.
Precisely. It's about comparing potential scenarios rigorously. And to manage all this data, the variables are organized hierarchically across 3 levels.
Okay, so it's got the logic for the question. It knows the evidence type needed. How does it actually get that evidence from the tree?
Through what they call scorer functions.
Scorer functions.
Yeah, think of them as specialized tools or subroutines designed to probe the MCTS tree, the states, the actions, and return specific values.
Like what?
Could be a number, like an estimated cost, or a Boolean, a simple true or false. They're tailored to the criteria defined in the logical query.
So for base level evidence.
The scorer might just navigate the tree to the right node and pull out the stored value. Pretty straightforward tree traversal.
And for derived evidence.
The scorer would perform calculations, like averaging values across a set of relevant nodes identified by the logic.
Right. And for the complex logic comparison stuff, using CTL.
They use specific CTL model checking algorithms. These algorithms are designed to systematically check if those complex logical CTL statements are true or false within the structure of the MCTS tree.
Wow. Okay. That sounds computationally involved, but necessary for those deeper questions.
It is. It allows for verifying complex properties about the MCTS exploration.
Now, this framework isn't just analyzing the OCTS algorithm in a vacuum, right? The paratransit system itself has its own rules, its own context.
Absolutely crucial point. You need domain knowledge.
How does the framework bring that in?
It uses a dedicated but relatively small knowledge base.
What's in it?
Key information about paratransit services generally, specifics about the MCTS algorithm being used, and details of the MDP set up the constraints, objectives, reward structure.
The specific rules of the game for this paratransit scenario.
Exactly. It's about 3,000 words organized into roughly 34 distinct chunks or documents.
And how does it know which chunk is relevant to my question?
Good question. It uses a technique called retrieval augmented generation, or ARGI.
RAGI.
I've heard of that.
Yeah, it's become quite common. They use an AI model, specifically OpenAI's text embedding 3 small model here, to understand the user's query. And then search that knowledge base to find the chunks of text that are most semantically related, most relevant to the query.
Like a smart search engine for the knowledge base.
Pretty much. It calculates a relatedness score and pulls in the chunks that pass a certain threshold.
So only the truly relevant background info gets used.
That's the idea. Keep the context focused. Okay, we've walked through quite a process. The framework gets the question, translates it to logic, identifies evidence type, uses scorers, sometimes with CTL, to get data from the tree, and pulls relevant domain knowledge using ARI.
Phew. Yeah, that's a good summary.
What's the very last step? How does this all turn into the nice natural language answer the user actually sees?
That final synthesis is handled by another LLM, specifically a question answering model.
Okay.
It's fed all the pieces gathered along the way, the user's original question,
Right.
the logical variables that were used, the actual results returned by the scorer functions, the evidence,
Ooh, data points.
and the relevant text snippets retrieved from the knowledge base.
So it gets the question, the logic, the data, and the context.
Exactly. And its job is to weave all that together into a coherent, easy-to-understand explanation in natural language that directly answers the user's query.
It sounds incredibly thorough, but as always, the proof is in the pudding. Did it actually work better than just asking a standard LLM?
That was the million-dollar question for the researchers.
How did they test it? What was the core research question?
Their main goal was clear. Does this logic-enabled LLM framework outperform standard, off-the-shelf LLMs when it comes to generating explanations for MCTS decisions that are both factually accurate and relevant?
And which LLMs did they compare against and use within their framework?
They used several powerful models for the evaluation, GPT-4, the newer GPT-4o, and also Llama 3.1.
Okay, top-tier models. What did the actual evaluation setup look like?
It was quite extensive. They created a data set of 620 distinct questions someone might realistically ask about the paratransit plans generated by MCTS.
620 different questions.
Yes, and each one was posed 3 times to check for consistency. And crucially, for every single query, they manually prepared the ground truth. Meaning they determined the correct question category, the necessary logical steps, the specific evidence needed from the MCTS trace, and they even wrote a reference gold standard answer themselves.
Wow, that sounds like a massive amount of careful preparation.
It really does, but it's essential for rigorous evaluation.
So how did they measure the quality of the AI-generated answers against these gold standards?
They used two main automated metrics, BERT score and FACT-CC.
Okay, what do those tell us? BERT score first.
BERT score focuses on semantic similarity. It compares the meaning of the generated explanation to the meaning of the reference answer. High BERT score means the explanation is relevant and covers the same key points.
So relevance and topical overlap. What about FACT-CC?
FACT-CC is specifically designed to assess factual consistency. It checks if the statements in the generative explanation are actually supported by the underlying evidence, in this case the MCTS data and the reference answer, or if they contradict it.
So it's looking for factual errors, hallucinations, that kind of thing.
Exactly. High FACT-CC means the explanation is factually accurate and consistent with the ground truth.
All right, the moment of truth. What were the results? Did the logic-enabled framework deliver?
The results were pretty dramatic, actually.
Oh, how so?
First, looking at the baseline, just using the standard LLMs, GPT-4o and Llama 3.1, without the logic framework. Their performance was, well, not great.
Really?
Yeah. The FACT-CC scores, measuring factual accuracy, hovered around 42% to 51%.
So roughly half the time they were generating factually questionable explanations.
That's what the metric suggests. And BERT score for relevance was also quite variable and sometimes low, ranging from about 6% up to 56%.
That really underscores the difficulty standard LLMs have in reasoning accurately about complex algorithmic processes like MCTS.
It absolutely does. They can sound plausible, but factual grounding is a challenge.
So how did the new framework perform when integrated with these same LLMs?
This is where it gets impressive. The improvement was significant across the board.
Okay, give us the numbers.
With the framework using Llama 3.1, the FACT-CC score jumped up significantly, a 2.4 times improvement over the baseline Llama 3.1. Factual accuracy went way up.
A 2.4x improvement in factual accuracy. That's huge.
It is. And using GPT-4 within the framework, they saw a 1.59 times improvement in FACT-CC compared to baseline GPT-4o, reaching over 72% accuracy.
Okay, so major gains in factual correctness with both models. What about relevance, the BERT score?
Even bigger gains there, particularly with Llama. The framework boosted Llama 3.1's BERT score by nearly 8 times, a 7.92x improvement.
Wow, almost 8 times more relevant.
Yeah. And with GPT-4, the framework led to a 1.7 times improvement in BERT score compared to the baseline.
So the conclusion is pretty clear then.
Extremely clear. The logic-enabled framework consistently and substantially outperformed the basic LLMs on both factual accuracy and relevance when explaining MCTS decisions.
That really does sound like a compelling demonstration. Combining that LLM fluency with logical rigor seems to be the key.
It really appears to be. This work provides strong evidence that this kind of hybrid approach is a very promising direction for tackling AI explainability.
It feels like a genuinely significant step towards making these powerful but complex algorithms less like black boxes.
I agree. It addresses that core need for transparency and trust, which, as we discussed, is so vital if these tools are going to be adopted confidently in high-stakes, real-world applications. Understanding the why matters.
Okay, so let's quickly recap this deep dive. We've explored a really innovative framework, one that cleverly integrates large language models with a formal logic system.
The goal being to explain the reasoning behind the Monte Carlo tree search algorithm, particularly in sequential planning.
And the paratransit planning test case showed it works, producing explanations that are way more factually accurate and relevant than standard LLMs can manage alone.
Yeah, the evaluation results were quite striking.
The big takeaway seems to be about building that crucial bridge towards trusting complex AI.
Exactly. By providing explanations in natural language, but explanations that are rigorously grounded in logical reasoning and actual evidence from the algorithm's process.
It tackles that core barrier of opacity.
It really does. It helps ensure human understanding and oversight remain possible, even as AI gets more sophisticated.
Which leads us perfectly to a final thought for you, our listener.
Right.
As AI like this becomes more and more embedded in critical systems, transportation, logistics, maybe even healthcare or finance, how truly essential do you think frameworks like this one, focused on transparent, verifiable explanations, are going to be?
And maybe think about other areas beyond planning where this kind of deep explainability would be not just helpful, but perhaps absolutely necessary for responsible deployment.
Definitely something to ponder. Thanks for joining us on this deep dive.